Okay, guys, so today we're going to talk about the unit circle. Okay, so now the unit circle is sort of the first thing that we need to learn about when we talk about the idea of trigonometry. So once we sort of cover this, we'll start to build up towards getting into the idea of basic trig. All right. So what I want to be able to do in this section is talk about how to find certain points that are on the unit circle. We'll talk about how to find um, where the radius is of a unit circle corresponding to any angle. And of course, we can talk about negative angles and angles that are bigger than one full revolution. We'll also talk about how to find the length of a circular arc, and we'll talk about how to find the coordinates of an endpoint for any radius of a unit circle. All right. Okay, so let's go ahead and we'll get started. So what do I mean by a unit circle? Well, in its most basic definition, the unit circle is just a circle with radius 1 centered at the origin, right? So we've looked at equations of circles already. And now if you're centered at the origin with radius 1, the equation for the unit circle is x squared plus y squared is equal to 1. All right, now we can use the unit circle to discuss a lot of aspects of trig, which is what we're going to do. Okay, so, and yeah, here's what I just mentioned. So the unit circle is made up of points where you have x comma y, and they of course satisfy the equation x squared plus y squared is equal to 1, right? Or else they're not on the unit circle. So with that being said, we're going to find in this first example points on the unit circle whose first coordinate is 2/3, right? Well, what does it mean for its first coordinate to be 2/3? That means that your x value is 2/3, and we want to figure out, well, what corresponding y values are there. All right, now we're going to use the fact that x squared plus y squared has to equal 1. And if we're assuming that x is 2/3, we should be able to find what y would have to be. Okay, so if x is 2/3, then I'm putting in a 2/3 in for x, and I have y squared is equal to 1. So now if we square 2/3, right, that's 2/3 times 2/3, or you can think of it as 2 squared over 3 squared, but you're getting it at 4/9. All right, plus y squared is equal to 1. Now, of course, to get y by itself, we'll subtract 4/9 from both sides. And if we do that on the left side, they cancel. So we'll just be left with y squared. And on the right side, I want to do 1 minus 4/9, which of course, if we find a common denominator for, is really 9 minus 4/9. So this will be a 5/9. Okay, and now of course to get y, I'll square root both sides, and we get that y is equal to plus or minus square root of 5 over square root of 9. And of course we can simplify that to plus or minus square root of 5/3. All right, so then that means that our 2 points are 2/3 comma square root of 5/3 and 2/3 comma negative square root of 5/3. All right, and of course this point here is 2/3 positive square root of 5/3, and this would be your 2/3 negative square root of 5/3. All right, so those are those first 2 points there. Okay. Okay, now in example 2, we want to find the points on the unit circle whose 2 coordinates are equal. All right, now if the 2 coordinates are equal, that means that x is equal to y. All right, so that's what we mean when we say that the 2 coordinates are equal. But again, our equation is x squared plus y squared is equal to 1. And if x is equal to y, then we could say, for example, that x squared plus another x squared, since x and y are equal, is equal to 1. All right, so this part here is coming from the fact that x and y are the same. Well, now if we solve this equation, these two will give us a 2x squared is equal to 1. And then if we divide by 2, we get that x squared is a 1 over 2. And then, of course, we can square root both sides. And we'll get that x is plus or minus square root of 1 over square root of 2, which we could say is plus or minus 1 over a square root of 2. But of course, we need to rationalize this. You can't have a square root in the denominator. So we'll multiply top and bottom by square root of 2. And this will give us plus or minus square root of 2 over 2 for our x values. Okay, but again, the original question was find the points on the unit circle whose two coordinates are equal. So for x, we have two possibilities. It's either square root of 2 or minus square root of 2 over 2. And if we want y to be the same, then the 2 points are square root of 2 over 2, comma square root of 2 over 2, or negative square root of 2 over 2, comma negative square root of 2 over 2. All right, so these are our two coordinates where x equals y on the unit circle. All right, so that's that example. Okay, now I then want to move on to talking about angles on the unit circle. Okay, now we're always going to reference our angles about this line right here, right? So this sort of radius from 0 to 1 on the x-axis. So radius from x equals 0 to x equals 1, which is also known as the positive horizontal axis. This is where we sort of assume our starting point for angles to be. All right, so whenever we reference an angle on the unit circle, we mean starting from this spot. Okay. Now, of course, you can talk about the other axes as well, but the one that we use the most often is the positive horizontal axis. All right. But if you want, you could also talk about the negative horizontal axis, which would be this one here. All right. So that would be the negative. Let's do it this way. Let's say this is 2. And then in orange, we did the positive horizontal axis. Now the positive vertical axis, if I call this 3, is this line here, this radius here. Right, because that's where you have positive values on your vertical axis. And then, of course, last but not least, we could say that the negative vertical axis is this one here. All right, but again, most of the time, our attention is going to be focused on the positive horizontal axis. Okay, so on the unit circle, we will be looking at, again, this positive horizontal axis. And all angles would be measured counterclockwise starting at the positive horizontal axis, right? So angles are measured in the positive direction at least. Counterclockwise. Let's try, I don't know why that keeps going. Counterclockwise from here, from the positive horizontal axis, right? And if it's counterclockwise, that's the direction of a positive angle. If you wanted to go clockwise, well, then you would have a negative angle, okay? So in this example, this happens to be a 45-degree angle. All right, and we'll sort of talk about how you can find these angles later. But here they tell us that this endpoint is square root of 2 over 2. All right, and this corresponds to an angle, a positive angle of 45 degrees. Okay. Now, of course, this sort of pushes us in the direction of For positive angles, we say that the radius of the unit circle corresponding to this is the Greek letter theta, which is usually used to talk about angles. All right, so that's the Greek letter theta. It's the radius that essentially you would draw when starting from the positive horizontal axis. You go that many degrees, of course, traveling counterclockwise, and that radius would then correspond to the one that's formed by that angle. Okay, so I want to look at the three angles of 90, 180, and 360. And I want to start with 360 because that's probably the one that everybody's most familiar with. Okay, so we know that 360 degrees is a one full circle or one full rotation. Okay, so if I start here and I want to go 360 degrees, well, I'm going to go all the way back here, and that radius would be here. Right, so it'd actually be the same as where we start. So we could say that this is either 0 or 360 degrees. Okay, now the difference is that if you didn't move, if you just stayed there, that's 0 degrees. If you go one full rotation around, that would be 360 degrees. Now, if 360 is one full rotation, 180 is 1/2 of 360, so this is 1/2 of a full circle. So if we're going 180 degrees, I must start here and end here, right? And then this would be my radius that corresponds to 180 degrees, right? And while half of 180 is 90, so let's see, let's see what will jump out. Let's use this light blue. So 90 is going to correspond to 1/4 of a full circle. And again, we're measuring this from this positive axis. So if I come up here and I go 1/4 of the way, this would be corresponding to 90 degrees. Okay, so those are the different radii that correspond to each of those three angles. Okay, well, now let's extend this and let's do the angles of 20, 100, and 200. Now, the way that I usually think about these is I first sort of think that this is 0 or 360, depending on if I don't move or if I go around one full time. This is 90 degrees. This is 180 degrees. And if you add another 1/4, or if you add another 90 degrees, you'll get that this is 270. Okay, now from here we can talk about what each of these are. All right, rather than thinking of it as 20 over 360 is 1/18 of a revolution, I think what you can think about is that 20 is in between 0 and 90. So 20 degrees is going to be in this first quadrant here. And then you can think about, well, what's halfway between here? Well, halfway between, right, this angle would be 45 degrees because that's halfway between 0 and 90, right? If you were to break this into three equal pieces instead of 2 equal pieces with the 45-degree angle, you can have an angle here and an angle here, and this would correspond to 60 and this would correspond to 30, so that each slice there corresponds to 30 degrees. And these are usually the three angles that we sort of can base everything off of, right? Well, now we can go ahead and we can talk about 20 degrees. Okay, 20 degrees is going to be between 0 and 30, but of course closer to 30, right? Because 20 is closer to 30 than it is to 0. So your 20-degree angle will be about here. All right, and then we could do something similar for 100. Well, what's a 100-degree angle? It's going to be a little bit past 90. So 100 degrees might be somewhere about here. right? And then finally, 200 degrees would be 20 degrees past 180. So I actually would come out the same direction here that I did on the opposite side, right? And you could make this as close as you want by doing this this 30, 60, and 45 separation in each quadrant, right? Okay, now let's talk about negative angles. Now, if you want to have a negative angle, you measure them the same way that you do the positive angles, only you're now moving clockwise from that positive horizontal axis. So if you're looking at positive horizontal axis, this way would be the direction you travel for positive angles, while you would travel this way for negative angles. All right, so let's do some examples of negative angles. Okay, so we want to look at negative 30, negative 60, and negative 90. And we'll start with 90. Now we know this is not 1/4 of a full rotation. And normally that would correspond to here, right? But since we're going negative 90 degrees, I want to travel this way, 1/4 rotation. So my negative 90 degrees will be here. And don't forget that earlier we called that 270 degrees. And we'll sort of see a relationship between them. Okay, now also what we did earlier was we said that 60 degrees would come from breaking that first quadrant into 3 separate equal pieces. And then you'd have a 30 and a 60 there. Well, if I have a negative 60, I'm doing something similar. I'm traveling this far, but I need to do it in the opposite direction. So negative 60 would be somewhere about here. Okay, and then similarly, we could say that negative 30 would be about here. All right, so it's just traveling in the opposite direction that you normally would. All right, so that's the idea for those negative angles. Okay, so to summarize, all of your angle measurements are going to start from the positive horizontal axis. If you want a positive angle, you travel counterclockwise. If you want a negative angle, you travel clockwise. Okay, now I want to go back and talk about what are some other angles that we could make here, right? So let's pretend that on the unit circle, let me just draw a circle here. And let's look at the angle 40 degrees, okay? So 40 degrees is going to be a little less than 45, so it's a little bit less than halfway, and I should maybe make this a little better. All right, so we could say that this is about 40 degrees. All right, but of course there are other ways that we could get there, right? So 40 degrees in the positive direction could also be obtained by going in this direction. By how much? Well, I would need to go 3/4 of a circle, and then between here I have another 50 degrees. So I need to go 270 degrees, which is the 3/4, plus another 50, which would give me 320 degrees. All right, and of course another way we could have gotten that is that we want to go the whole circle except for this 40 degrees. So you could have also said it's 360 minus 40, and that could have also been 320. All right, now that's not the only other option we could have done. What if we went around one full time and then another 40, right? So then that would be 360 degrees plus 40 degrees, right? And that would be 400 degrees. All right, we could also do the same thing in the opposite direction. I could have gone, let me try and do this on the very inside. So I could have started here, gone one full rotation negative, and then come back here. right? So I could have gone minus 360 degrees and then minus another 320 more that we got before, and that would correspond to minus 680 degrees. Okay, so there's an infinite number of ways that you can get to the same angle, right? And that's what we're going to summarize here in this result. So if you have an angle given in degrees, so theta is an angle on the unit circle, then you can add theta to any multiple of 360, right? So this is just any multiple of 360 added to that angle is equivalent. Okay, so that's something that we can use quite often, right? So that will come up a fair amount. Okay, now I want to discuss how you can find the length of a circular arc on the unit circle. Okay, so if you're given an angle, right, of theta degrees on a circle with radius r, then the length of the arc, and I'll show you what I mean by that. Let me just draw this out. Okay, so let's say that I have an angle, and this is theta degrees, right? And then I have some radius of the circle, which is r. Now, when I say the arc, I mean this little sliver of the circle right here, right? And so to get the length of that sliver, you're going to take pi, you're going to multiply it by your theta and times your radius, and then divide that by 180, right? So let's look at that. Okay, so in this first example, we want to know what is the length of a circular arc on the unit circle corresponding to 90 degrees. Well, we know that this arc has the length equal to theta times pi times r over 180. Now, in this case, our theta is 90. Our r is 1 because we're on the unit circle, and pi is just some number. So the arc is going to equal 90 times pi times 1 over 180. And for the most part, we usually leave our pi's in our answer, and we just reduce our fraction. So 90 over 180 would, of course, be 1/2. So we could say this is an arc of pi over 2. All right, so that's the length of that arc there. Okay, so that's that example. Now the next one is similar, but now we're going to sort of apply it to sort of a real life object. So the London Eye is a giant Ferris wheel in England with a diameter of 394 feet. So we have this circle, and diameter is all the way across. So we have that this length is 394 feet. Okay, now we're told that it rotates 12.3 degrees each minute. Okay, and we want to know what is the speed of the passengers on the outer eye of this circle, or outer edge, I guess I should say. Right, well, how do you get the speed of something? The speed is equal to the distance over time, right? Now, so in order to come up with this distance, we need to find the length of the arc per this rotation, right? So we're going to use this 12.3 degrees each minute, and we're going to find how much that is in feet per minute, right? So in feet per minute, this is just the length of the arc. So this is theta times pi times r over 180. So our theta is 12.3 times pi. Now our r is not 394 because that's our diameter, right? Our radius is half of that. So half of 394 would be I believe a 197, right? Right, and we want to divide that by 180. Right, so the length of this arc, if we punch this out in the calculator, so if I do a 12.3 times 197, and I divide that by 180, we get that this is about 13.46 pi, which if we multiply this by pi, we're going to get that this is roughly 42.29. So the speed is 42.29 feet per minute. Right, so that's how fast that the passengers would be traveling on this Ferris wheel. Okay, now the last thing that I want to discuss in this opening section on the unit circle are two special triangles. All right, so the first triangle is what I'll usually refer to as a 30, 60, 90 triangle. So of course, this is a right triangle that has a 30-degree and a 60-degree angle within it, right? And of course, since it's a right triangle, you also get a 90-degree angle. Now, at some point in a geometry class, you probably learned that the relationship between these three sides looks something like this, right? So if your hypotenuse, or the longest side of the triangle, is 1, then the side that's across the 30-degree angle is 1/2, and the side that's across the 60-degree angle is square root of 3/2. Right? So this is something that will be very important moving forward when we look at the unit circle. Okay, so here's what we can do with this. So now in part A, we want to find the coordinates of the endpoint on the radius circle that correspond to 30 degrees, and in part B to 60 degrees. Okay, so let's do first part A. We'll look at the 30 degrees scenario. So of course, let me get my unit circle on here. All right, we'll all pretend that that's a circle. So 30 degrees looks something like this, right? But if we're careful here, I can put my triangle in there that we just had, right? So of course, the angle that's in here is 30 degrees. This is a right angle, and that doesn't leave us much choice, but this angle has to be 60 degrees. Now this length here is just the radius of the circle, so we know that that's 1. And now what are these relationships here? Well, this is what's across from the 30-degree angle, that's a 1/2. And what's across from the 60-degree angle, that's a square root of 3/2. All right, but what did we just find here? Well, we just found the coordinates of this thing. Because its x-coordinate is this distance, which is square root of 3/2, and its y-coordinate is this distance, which is 1/2. So this is the point that corresponds to 30 degrees on the unit circle. All right, let's do the same thing, but for 60. Okay, so if I draw my unit circle, then 60 degrees, of course, is somewhere up here. But by the same logic, I can drop a vertical line here. This angle is 60 degrees. This is a right angle. Let me zoom in a little bit. And of course, that leaves us that this has to be a 30-degree angle. And again, radius of the circle is 1, so that's this hypotenuse. Across from the 30-degree angle, I have 1/2. Across from the 60-degree angle, I have square root of 3/2. But again, this is just my y value, and this is my x value. So this point this coordinate is 1/2 comma square root of 3 over 2. And that corresponds to 60 degrees. Okay. Now, the other triangle that you should be familiar with that the book leaves out here is the 45, 45, 90 triangle, right? So if you wanted to find a 45-degree angle, you want to find the points corresponding to a 45-degree angle, you'd have something like this. So 45 degrees is here. And if you drop this perpendicular down, this is a right angle, this is 45, and then this has to be 45. So of course, this radius is 1, and by our triangle here, these are each square root of 2 over 2. So what's the point corresponding to 45 degrees? It's square root of 2 over 2, comma square root of 2 over 2. All right, so if you can remember these two triangles, a lot of people are usually taught to memorize the unit circle, but if you can memorize just these two triangles, you don't need to memorize the unit circle. You can always figure out what your angles are from these two triangles. All right, so that concludes this video on an intro to the unit circle. I hope you enjoyed, and I will see you next time.